Oh, where's the best place for me? That's pretty good. Oh, my mic. It's open. Okay, great. Welcome. I'm Kingdon, the host. Let's do some conditions stuff. Okay, so what are conditions? What are we here to talk about today? We're going to talk about Kubernetes operators. So we have a Kubernetes operator that we've been working on here. You can read more about it in the description. And in this operator, we started to build a few different condition pattern. Let's see, what did we do? So in order to implement conditions, you need to have first CRD in Kubernetes. The CRD needs to implement the conditions structure, which we'll see here. Let's take a look. Okay, so this is not the condition structure, but this is something you can do as a side effect of the condition structure, which is reporting on ready status, for example, if you use the ready condition, or the ready type condition. So what is condition struct? Our condition here, this is conditions. Conditions hold the condition for your resource kind, whatever type of resource that might be. So conditions carry with them a message, a last transition time. The last transition time records when the condition was updated. Observed generation represents the metadata generation that the condition was set based upon. Reason description contains a programmatic identifier. So the reason is a programmatic identifier for the programmer, but it maps to some human readable message. And condition true or false relates to the polarity of the condition, which is a little bit outside of the scope of what we're going to talk about today. But so conditions will help you to know about the transitions that your resource goes through. There are a few basic conditions that you typically implement first. Like we talked about just a moment ago, the ready type condition is a popular one. If your resource can go between ready and unready states, like a deployment, that's a helpful condition. So let's do some live debugging. Let's see if we can get an instance of this. So we've already got it running in a couple of different places. The most important place that this runs is on GitHub Actions. You can see it runs every hour. And in this workflow, we're just spinning up a little Kubernetes cluster, a little kind cluster, running Ruby locally. So we're running the controller outside of Kubernetes. But we need a Kubernetes control plane for the controller to use. So normally you would host the controller on the Kubernetes cluster. And we have that deployed in a couple of places as well. Let's see one of those in our terminal. Okay, we've got our dev stats controller here. got all of our leaves. These leaves happen to be stuck. I'm going to find an issue about that. Here it's possible for resources to get stuck. So we can read about those leaves here if you're interested. I've been curating issues to know what's wrong with the controller. So I'm trying to make this the best controller that it can be at this point for the 0.2.0 release. Because right now it does its job just fine, but it's just not a very good controller at this point. It does implement conditions marginally in a place or two. So we're going to go in and we're going to look at that in the running controller. So in spite of these resources being stuck, the controller is actually working. And by stuck, if you know how controllers work, you're probably balking at this. What do you mean it's stuck there? It says status OK. Isn't that good? I think that is okay, actually. But the way that this controller is set up, the way it's supposed to work in the cron job is, so normally controllers aren't implemented as a cron job either. I'm aiming to build a sort of a serverless controller. And I'm using like a poor man approach along the way. So like the GitHub Actions deployment of the controllers actually are, for me, effectively serverless because I don't have to host a server. I don't have to own any resources to do that. It can run every hour. GitHub Actions doesn't really care, and it's free. But at some point they may care here, and so this is what happens. So once every 4 minutes, I think, yeah, it's 11:44. The controller is supposed to come along and reconcile all of these resources together. And the reason is because we're going to take a measurement. So these resources represent a flux component. Let's look at like source controller, for example. Oops. So this controller also only operates in the default namespace right now, which is a little bit strange for a controller, but like I said, it's not a very good controller just yet. Getting Slack notifications here. Just want to make sure it's not someone trying to tell me that my fly is down or something like that. Sorry, this is live. I'm going to check on the chat too, since this is live. I'll make sure that if anyone is trying to tell me that my fly is down, I would see. Okay. Alright, so yeah, so I've been documenting these issues as I come along, and as they're not so much in the way that I need to fix them right now, I can live with just one namespace. I only have one org to monitor, the Flux CD org at this point. So this controller could grow over time to monitor multiple orgs, but right now it doesn't need to do that. It just needs to monitor the Flux org. And what I mean by monitor the Flux org, this number here, this count, comes from a page on Flux CD packages source controller. Yeah, not that one. Here, so this number, we're interested in this number, we want to know, and I don't know if you saw that, but that is pretty close to the number we see here. Oops. I'll get this out of the way too. So every time that reconciles, it's just going to check that number. And turns out this number isn't available in any public API, so we have to go and scrape this HTML page in order to obtain this number. But that's what the controller does, or at least that's what one of the controllers does. We have a couple of controllers here, and you can see these pods run to completion every 4 minutes. And there's another one coming soon. So let's watch the logs live. Here we can see there's also a web server running that maybe the health check is trying to hit this web server, and that's why we're getting a message about cannot render console. Okay, here comes our controller. It's running. Let's see how much of this we can squeeze on the screen, since it's going pretty fast. So that's the good news there. That's what we're hoping the controller does every cycle. It gets to the point where all 16 packages are ready. And how does a package become ready? First, in an asynchronous fashion, all of the pages are fetched simultaneously-ish, and then they're parsed, and we find that number, and we update the status simultaneously-ish, concurrently, sort of. I don't really understand fibers perfectly, but we'll understand them together at some point. So anyway, doing the thing here, this is scheduling a fiber and patching new generation into the status. So that's the job that runs, and we can look at that job. Runs inside of the Ruby Kubernetes operator framework. Here we go. Here's our source code. So we'll look at project reconciler, leaf reconciler, and reconcile leaf. And we'll look at my WASMer, and we'll look at tests. And then we'll look at sample. And we'll look at PKV, sample, and package, version reconciler. And we're going to want to see operator utility in AR base too. Why not? Why not CLI when we launch this thing too? So we'll see all these source code files. Hopefully I didn't skip anything. That's a pretty reasonable order to go into. Okay, so project reconciler. I'm going to go through this in a really abridged, abbreviated fashion. We've got a run method, we've got upsert, and there's a delete method down here. And then there's some other stuff. Create new leaves. So a package's main responsibility, project's main responsibility is to have packages under it. So project is a GitHub organization, like FlexCD. And then package is like source controller. And these are called different things in different places. Here they're called project and leaf. In the active record models, they are called package and GitHub org, or GitHub org and package. So, I'm not going to talk about that in any detail other than to say that if you look at Kubernetes operator itself, where this is the Ruby gem that I use to implement Kubernetes operators. Thank you, Tobias, for publishing this. If you look at this in the example, it's very slim. There's not much here, right? We've only got this one gem. So we're showing what we can do with this gem here, and that's what we're using to do what we're doing. It's really easy. We've got an upsert method and a delete method, like I said, and that's what we have to implement. That's what our responsibility is as a consumer of the Kubernetes operator gem. So whenever a new resource gets created, we'll get a message. And then we have to figure out what else we're supposed to do, basically, which is to run the Kubernetes operator that does that response pattern. So what's missing from this, I guess, is it doesn't really handle pre-existing resources pretty well from what I can tell. So that's kind of where my code gets a little bit more complicated than this. If you read my code, that's really what I'm doing. I'm trying to handle upsert, but in a dynamic way. So if I get an upsert, I know that means there's some synchronous work to be done. And by synchronous, I mean I need to finish some download and parse operation before I can write out the number that I'm supposed to return as a result. So that's what I mean by synchronous. We need a response from it. And upsert is supposed to handle that, I guess, if that's what your resource is supposed to do, but in a way where it's scheduling the work so that it can be done concurrently. So we're using the conditions pattern to achieve that sort of concurrency. Basically, whenever we get an asynchronous part of the synchronous job, so we're building, like, this is the regular pattern here as I understand it in modern asynchronous programming, is when you have a method that needs a synchronous response, you don't block the entire time that you're doing work. You know, there are other parts of your program besides the thing that's waiting for this synchronous response, ostensibly, and they should be able to work while you're doing this. So that's what fibers enables. And Kubernetes operator doesn't implement fibers natively here. It's just a serial process. So if you get 16 resources, each one is going to be upserted. It's going to call the upsert method, and all of the other calls to upsert are going to block behind it until we're done handling the first upsert. So it's really to our benefit to be done as quickly as possible in the most significant way that we can do. And what we're doing with the condition pattern to make this work better for us so that we can do more concurrent things and let things that can happen in the background happen in the background, and by that I mean I/O. We can wait for some I/O while we go and process some other event. As long as we're not depending on the output of that I/O, we can let that I/O process in the background. So that's what mainly differentiates my Kubernetes operator code from the example here. If we look at it in a little more depth, we would see that. But so here's our project operator. Like I said, we have a run method, so we expect the project operator to be called run, and when it gets run, it gets one of these AR base connections. That's another one of the class we're going to look at, with a pool size of 0. That means it's actually not connecting to the database at this point. It doesn't need a database connection for anything it's about to do. So what do we have a database in our Kubernetes operator? That's a good question. I'm not going to answer right now, but think about that for a little while. We do have a database connection here, though, or we have the potential for a database connection anyway. So we're incorporating the Rails gem. That's another thing that the Kubernetes operator didn't endeavor to do, the Kubernetes operator upstream gem. So what this code says it should do, T's are coming out of create new leaves. So when we call this create new leaves method, it populates this T's, and we get a count value out of there as well. And that count is something we're returning in our status here on the project. So the count tells how many leaf resources it creates. And there's no accounting between parent and child here. This, like I said, it's not a very good controller, but it does create a leaf for each of those T's. So, and it does it in a synchronous way, not an asynchronous way. So this is the project operator, and it runs serially. It does not use fibers. Okay, so this is good. It's a good first example. Then we have this delete method, and the only thing that's notable about this delete method is that we do attempt to clean up after ourselves. So when the project resource gets deleted, the packages that it created should get deleted as well. And that works like in a cascading fashion. So there's no configurability for that. It's just a thing that we do. And then it's a register health check method. I think I thought that I would need fiber here. I wound up putting it somewhere else. So this register health check method doesn't do very much. It just saves the package count in the connection using, so this does use the database connection. So I wonder if it's a problem that we initialize this with a pool size of 0 or if it's okay. I'm not really sure. We'll get back to that. But anyway, so we're debugging today. So we're going to run this code as soon as we can. So let's try not to spend too much time analyzing every part. So this is the leaf operator. And the leaf operator has a few more things besides a run method, because it is meant to be run concurrently. So I guess the reason that we wrote this pool size a bit in here was so that we could initialize our Kubernetes client without initializing the database connection. I think that's what this is for. So when we fork our process under each fiber, we may need to use the database, and we don't want to have a stale database handle hanging around from the connection that our parent process had open, which is a possibility that you can have. I think I've seen that error happen in here. That's why I introduced that code. So why did we introduce a database into here? I'm going to talk about that for a minute. So the reason why I added a database was actually because I was very concerned about control plane performance, and I was concerned about creating a stateless operator that can return metrics and status. So I think that I need to be able to hold information for longer than a single request, and I need to be able, so what a request may be a reconcile cycle. I need to be able to hold information around for reporting for metrics purposes, and I'm not exactly sure how to do that yet. But I know that if I have a database handle around, and if I have a number that I want to record somewhere, I can certainly put that number in a database. I know how to do that pretty well. I've done that for 20 years at this point, probably, using databases from programming languages like Ruby. So, and I know that I can retrieve data from the database without incurring a major performance penalty, which I'm not sure about with Kubernetes. I think that sometimes I may need to exercise some of the more complicated things like informers or a notify pattern to see good performance in Kubernetes. I'm afraid that I can't just fetch a resource as many times as I want without impacting performance somehow, and that if I make my controller too stateless, then it will cause a performance problem for me. So I don't really know what I'm doing is really the bottom line. So I put a database in here because it's something that I am familiar with, I'm comfortable with, and I know that it has predictable performance. Whereas my control plane, I don't know as much. I'd rather not read from it again once I've written to it. Just write my information to it, and then keep my own copy around in case I need it. That's really the bottom line. Why did I use a database? So that I don't have to fetch information that I already recorded in the Kubernetes and wonder if it's changed since I wrote it or not. But at some point we should write the database out of here, I think, and do most controllers don't have access to a database, so that's pretty unconventional. Okay, so handle reconciling. Where is handle reconciling called? If is already reconciling, patch equals handle reconciling. Is marked as reconciling from a previous call to upsert. Okay, so what happens here is every time we make a little bit of progress, we write an update into the conditions about it. And then we use that little bit of progress to tell us which part of the upsert method we should skip or which part we should proceed through. And I'm not really confident about the structure of this, other than to say that it seems to work. After a lot of fiddling, I got to this point, and it does seem to mostly work. So what we would want to do is figure out why those resources are stuck. That's what we're going to debug. Because they shouldn't be stuck, and we'll see why they shouldn't be stuck in a minute. Well, let's see, this is reconcile leaf. So this is what actually happens when we call that doing the thing part. So we've got a Kubernetes client. What is this? Reconcile async. We call the reconcile async method. And this happens in, where are we? This is reconcile leaf. Okay, so R comes from get current stat with time. And get current stat with time is calling into that my_wasmer that we saw before. So if you've been following the story, we built a Kubernetes operator to run WebAssembly in. So that's what this is. Let's see. There, my_wasmer. So get current stat with time calls into wasmer current download count. So we said we're fetching a HTML page, and it's been done by the time we get to wasmer current download count. We already have the HTML. So here's our HTTP client wrapped that just does project repo image HTTP client call. So we can provide our own implementation of HTTP client in the get current stat with time method, and then we return back the time and the count. And probably not very useful to return the start time alone. Maybe we want the start time and the end time. But I'm not going to worry about that right now. Okay, and so what are we doing once we've got the HTML file.join? So we are writing it into a file. We're creating a temporary file, target directory, file to join content dir repo image, and file.join target dir content. IO.write cache file equals expand path target dir file name file. I think this is the file that you ran, and then the cache directory is in that directory, the directory that contains the file that you ran. I wrote this code, so at least I think I did. Alright, so then we're writing this to a file, and we're doing that so that we can pass the file into the WebAssembly as file system context. This is a sneaky thing that I've done because there is no string type in WASM, so I cannot build a WASM module that I can pass a string of HTML into. As far as I know, this is impossible in Ruby, or at least it would require a fair amount of pointer arithmetic that I don't want to trouble myself with, and memory allocation. So I'm using a file, and I'm passing it in, as a mapped directory. Okay, and this is the argument here. So the content, HTML/content, gets passed in as an argument to this WASM. And let's look at the WASM while we're here. It's a shame if we don't look at the WASM itself. Okay, we've got as much time as we want. This is our live stream. It's not the 30-minute talk at OSS Summit where we only have so much room. We can't look at things in detail. We're going to look at it. Okay, so here's the stat library, and this is where I implemented the WASM module. I originally was trying to put Ruby into WASM, which is a thing that you can do, but it didn't make any sense to put Ruby and WASM in Ruby. So I eventually decided, I broke down and I decided to learn a little bit of Rust to do this. So let's just look and see what we've got here. We've got cargo.lock file, so we've got some dependencies we pulled in. There's an HTML parser that we need, but the HTML parser itself is actually implemented inside of our own library that we've implemented called libstat. So this is the only dependency that we have here at our top level WASM. And we'll go and see that lib now. So there's source, main.rs, and there's libstat, which does have some dependencies. WASM bindgen scraper. Did we see dependencies in the other one? Let me see here. I'm not sure I really read that correctly. Dependencies. Libstat. No, that was our only dependency, is libstat. Okay, so scraper and WASM bindgen. We didn't actually wind up using WASM bindgen. I couldn't figure out how to get it to work. With bindgen, or the purpose of bindgen is to take your library and use it as a library in your WASM implementation. So instead of that would have been so that I could actually call it as a function instead of calling it as a WASI module, but I did wind up using WASI instead. So WASI is the WebAssembly System Interface. So my program is printing the results to standard output, and then Ruby is capturing it. So this is where I got myself into trouble partially, I think, or at least where I helped find the solution, was that in that particular context, it's not actually safe to do a multi-threaded approach, because in that context, WASMer doesn't actually have a way for you to retrieve the output in the Ruby gem. There's no Ruby gem fork and exec WASM that gives you back the output. It just passes standard output along, like we're forking a process, because we are. Or execing inside of the process at least, and it gets our current context. So in libstat, here's our library, and this is the function that we wanted to be able to call and pass in a string, which can't apparently do in WASM. We've got our count from HTML that just returns a number, and it returns a number in a 64-bit number. And we've got a HTML parse document. Okay, so we've got let content equals HTML, scraper, HTML. So I don't really understand what I'm doing here. I put the ampersand because it seemed to be important for the typing. Rust was very helpful at making this easy to write. I hope it's correct. But it compiles and it runs. So I'm pretty sure that nothing can go wrong. Famous last words. And there's some little manipulation of the DOM tree. Once we find the node that we're interested in, we need to find a node that has the data that we want relative to that node. So it's a little bit complicated what happens here, but it does eventually unwrap a number, x.i, and it returns x.i. And then outside of here, so that's the Rust primer. If you've never done Rust before, that's my little first Rust function that does anything useful. And then in our main program, we use that library function, count from HTML, and we use our standard environment. And I'm following this WASI example that I found on the WASMA Ruby. So WASMA Ruby coached me to try Rust, I think, is what happened. So what are we doing in here? Well, we're collecting some arguments. Remember we said we're going to pass an argument. That's the file to read. So let file source equal the first argument. In the remaining arguments, after we take away the first argument, which is the file that we ran itself, our WASM. Okay, so this is the remaining arguments, or the second argument at least, the file name that we passed. And then we read that file, or we return an error if the file can't be read. And count from HTML, we print that. I don't know what this does. I guess prints a number. I must have looked it up. But yeah, okay, so that's pretty cool. So we parse an HTML file and we print a number that is at a predetermined location. That's not very complicated. Back to a regularly scheduled program. Okay, so import object here. We're doing it in a WASI environment. WASMA instance, new module, import module. And here's the risky part that I was talking about, where we capture the output. And if we're switching contexts when we do this, or if we try to do this in the middle of a binding.pry session, well, we're going to not see our own output anymore. So that would be a problem for debugging. So we did say we're going to try to debug this interactively today. So I'm going to show a trick that makes it possible, even with all these concurrent processes running, to do debugging interactively in Ruby, which is one of the really nicest features of Ruby, I think at least. Okay. So that's our little myWASMer. And that is what happens when we call getCurrentStat with time, which happens in reconcile async that gets called from where did it get called? Reconcile async gets called from reconcile. Alright, so the async part happens where? Where are we doing anything asynchronous? When I'm looking for fiber, I don't see that there is anything happening asynchronously here. That is interesting. I wonder if that's because we've broken it up into all synchronous operations, and that's really how this works now. I really wanted to do one of these broadcasts before I made it super complicated. I'm afraid it is already too late. It was supposed to... Alright, well, we haven't gotten to the super complicated part yet, so there's still hope. Okay. Alright, so this is the function that gets called to reconcile one leaf. And here is actually what runs. That's what we want to see, right? This is actually... Oops. Let's go to the next file. Okay, so when we call this file, we're running it. We're actually running it. Because it needs to run in a fork. And... sorry, not in a fork, actually in a new process. That was what I figured out at some point. So here's our little myWASMer library. We already saw part of this. Here's our capturing output. That little handle that we saw earlier that we call, that makes sure that the output from whatever it is that we're doing gets captured, and then that we can put the standard out and standard error back when we're done. And here is a test scaffold that we can run get current stat with time in if we're not confident that it works yet. So this is where this function was first developed and tested. Okay, and sample. So this is where it starts to get into why this is not such a great controller. So sample is what we call, instead of calling the controller directly or alongside of the controller when we call it directly. And sample's job is to make sure that actually the sample record is loaded. So we're running this in test mode everywhere, basically, is what I'm saying, because this is the test sample. This is the seed data. And if we look at this, deploy bases test sample.yaml, we see this is the seed data, and we're really only interested in one thing from this seed data, which we can see if we go a little bit further, is we're only interested in the project of kind project. Okay, so if it's whatever it is, if its kind is project, then it is a project, and we can proceed into the rest of this code. So this leaf gets ignored here. We're not actually creating the source controller leaf from this file, but we're creating the project, and that is what calls the very first upsert that kicks off the entire pipeline. So when I say it's not a very good controller, it doesn't listen for existing resources. It only listens for upsert. So if you don't apply this resource after the controller is started, then it will never see anything, and it won't receive an upsert event. And upsert will never be called, and that would be a problem. So what I thought the controller should reasonably do, we need to have some logic around interval and reconciling so that the controller can proactively subscribe to all of the resources that it's supposed to manage. So the project controller would open an informer for every project in every namespace, and it would start processing upserts, but it would also process the records that are already present, but it would only do it once every period. So regardless of how many times, each time upsert is called, upsert gets called. Each time the record changes, upsert gets called. But the fun part is that we're also writing back to the resource when we update the conditions. So we're writing to the conditions to say this resource has progressed to a next stage of a next phase of the reconcile. And each time we do that, we're scheduling another call to upsert in the queue, right? Because we're writing back to that resource, and the resource has to reconcile again every time upsert gets called. So this is where I think we're probably diverging a little bit from the design, because most designs will probably try to reconcile the resource all the way through. We'll run back to back to back because most controllers aren't written in languages that only have a single main thread. So if I want to avoid reconciler that runs 4 concurrent reconcilers with some sort of a leader passing to each reconciler, here's the resource to reconcile now, here's the resource to reconcile now, so that each resource reconcile request only goes to one, and they can each do their job concurrently using all of the locking and whatever locking is necessary. I don't know if there's any locking necessary, or if there's each resource would be reconciled concurrently, like literally concurrently. But in our case, we're using Ruby, so the only things that we can do concurrently are the non-blocking operations. So all of those status writes, all of those synchronous things that we need to return results to, the determine the next thing that happens. Those things are not going to be able to be done concurrently. So, all right. So this sample creates the first record, and here, PKV sample. This is where I said we're going to make this more complicated. We want to explain it before it gets too complicated, but just know that there is a parallel structure that is developed for package versions. So initially we said we were only interested in download counts for each controller at a top level. That was the download count here. But then we said, actually, what we're really interested in is this package count too. We like to know how many downloads each published package got. So I said, okay, sure, we can track that too. So I built another parallel structure that actually turned out a lot simpler than the first one because it has fewer steps in the reconcile process. But anyway, we're not going to talk about that. We're just going to show it. So here's our package version operator. Version measurement is similar to measurement in the other controller. We didn't look at measurement, but we're want to get into the code. Okay, so here's our operator utility library. Here are some functions that I thought I would need in my operator that I wound up needing a couple of times, so I pulled them out here. Some of them I think are not used. And then here's our base connection class that really has two jobs. It has the job of providing us with a fresh Kubernetes client each time we ask for one, which may mean that we're garbage collecting an old client if it's fallen off the table. And also it has the responsibility of conditionally providing us with a database connection using the database configuration from Active Record and Rails. So we'll go out and load the configuration hash based on whatever Rails env says we're in production or non-production environment. We'll use the correct database connection handle for our environment, and we'll connect to a database conditionally. So if the pool size is 0, then we won't actually establish any connection. But if config pool is 0, if it's greater than 0, then we will connect and we'll actually have a connection around. So this way we avoid creating a connection before we fork, since we'll need this connection handle later. I had some concurrency issues in the earlier version of this, so there's a lot more fork. Like, I didn't initially intend to fork at all. I thought fibers would be everything I needed, but it looks like there's some issues. So here's our CLI. This is our actual entry point. And don't look below here. This is the more complicated stuff that's actually simpler, so don't worry about that just yet. So we've got 4 entry points, and we run them all, or we almost run them all. We run sample instead of project because we actually want that sample record to kick things off. But if we wanted to use this like a real true Kubernetes operator where the user declares the intents by creating our custom resources, then we would use this instead. And we'll switch to that at some point, probably not today. And then down here, like I said, this is actually simpler. We didn't need 4 handles for this one. We've just got 1 sample and 1 package version operator. And we run one or the other. It doesn't need to run both. It just does its whole job in a single pass. Because there are fewer fetches that need to happen. Because, I don't know if you noticed this, but all of these, we can go to the page here and we can see all of these versions, probably all of the versions for the last year with their signature. almost the last year. Here we can see each of them. And so we've got all these numbers to parse on a single page. So we don't actually need a big complicated assembly for doing concurrent operations because we can parse this entire file at once without multiple round trips. Okay, so we said we wanted to run it. We've got one running, but we're going to run it interactively. So let's take down the cron job here. So here's our Flux customization. We're deploying from an OCI repository called statsdev. That just runs from the latest version, so that might tell me something important later, depending on how we want to update this. I think we're just going to suspend the cron job. Let's see. Can we do this? Really? You're gonna do this to me right now? We gotta move this thing out of our way. I don't know why it just decided it needs to be on this screen. Oh, now it's back on the other screen. All right, forget it. What is the right output path? I need to have the Docker thing in here to do this. I need to have this is gonna break. Shoot. I need a fresh terminal for this. Oh. All right, good. Okay, we've got that artifact pulled now, so we can do our Flux build test. So we're going to make a little change to the artifact. We've got stats tracker dev. We're building from the path overlays dev. Great. Is that right? No, it's not right. Namespace. There. Okay, so here we've got our cron job. So we want to add a patch for our cron job that has a suspend field in it. Great, we can test that now. What just happened? It's called Stats Tracker GHCR. And we want to replace spec.suspend value true. Maybe we want to add this value, I guess. Let's see, did that work? Yes, there we go. Okay, and if we do test apply, we don't get any errors here, do we? I don't know, can't really tell. That looks pretty good to me. Alright, so we're going to add that. That's going to stop our cron job for a little while. Some kind of Dhahmatu Sahbati. A loud noise. Alright, is it suspended now? Suspend, true. Good, it is suspended. Okay, so if we want any more stats tracker to run, we're going to have to do it ourselves. So let's go run one and see if it does the same thing that it's been doing. And how do we run this? We use the proc file, and if you don't know how does the proc file work, you run foreman start. But we're going to run it with a couple of flags so that we get nice output. We actually want time, foreman start, no timestamp. Okay. So you see how it runs? Here, measure comes along and it says, oh, none of the packages are fresh. And this one comes and it says, oh, I'd like to run stat.wasm, but you haven't compiled it yet, so I'm not going to work. And then that one is going to happen over and over again until it fails utterly. We have to stop this. Hold on a second. So remember that stat library here, we can compile that. We want to run make here, but first we have to make sure we have cargo in our environment. Make okay, the test passes. There's our source controller count. Okay, let's try that again. Okay, foreman start. We may not get around to implementing our condition pattern update today, but we are going to see how conditions get written in the current implementation. And we may need to pry one of these resources open to see it happen interactively. Let's see. That might be a good idea. So this is happening pretty slowly because in part because we're not on the target cluster. So I think we're actually getting rate limited by the cluster itself, which is slow. It's low, but it's a lot slower when it needs to consult with your JWT to see whether or not. Yeah, and at a certain point, it's going to be ready, I think. Here it says stalled rescheduling. That's not something that happens in production. I'm not sure why it looks this way. But we're going to debug it a little bit. We're going to pick the most interesting point that we want to see interactively, and then we're going to put in a pry statement there so we can pry the context open. Use local cube config. So you see each time it creates a new fiber, it's creating 2 cube clients at the same time. That looks like an error, looks like a mistake. When I tested this before, it was always picking up after a while. It would be a little bit faster. Maybe it's because I'm doing video encoding that this is slow. That is entirely possible, you see. That may make this challenging, but we're going to try it. Alright, so what we want to see, I think, we want to see, yeah, alright, it got to the end, and it says, I'm not apparently going to finish in time. It expects these things to all become ready at about the same time, and then it can pass the event on to the next piece that's supposed to do the measurement and the snapshot of all the things with their ready states together. The class picture. Wonder if we have any chat participation going on here. Let's see, where did it go? I hope my fly is never down again, seriously. Alright, so what's supposed to happen when it fails or succeeds, it is supposed to issue a delete. And we want to see it clean up after itself before it finally terminates and quits. But it says 16 leaves still left, still collecting. Leads me to believe that it's not doing that, and it hasn't been doing that for several days, so I'm not sure why. We are going to look at the production environment too. There's a production environment where it doesn't run, or it does run. I'm not sure if it runs. I think it's also disabled, like as in suspend true. So, well, guys, I'm getting tired. So let's put a debug statement in here and see it working. What we want to see, I think, is when we get to the thing that we're interested in debugging. Here, we want to know. Where is the delete command going? That's what we really want to know. I don't see like a bunch of 404s or anything. I don't know why it would fail to delete. It sure does look like it's looping infinitely though, doesn't it? Finally gets to the give up point where it actually terminates itself. So I want to pull up the, try to remember where did I find this information. Yeah, here we go. Great, I was able to find it. Yeah, so this is the trick you need to know. If you've got fibers running concurrent code and you want to stop all the fibers from running while you inspect what's going on in your binding.pry session, you need to know that you can run binding.pry in a blocking fiber, which will prevent any other fibers from running. But wait a minute, Kingdon, you say, that's not what I want to do. I don't want to prevent every other fiber from running. I want to actually see what's going on while it's happening. I want to be able to interact with the fibers while they're running. I don't want to stop them. The fibers are the problem. I need to see what's wrong with them. So if we just want to make sure that we only run one binding.pry at the same time, we can put our call to binding.pry into a mutex and synchronize. So we just have to make sure that everyone gets the same mutex, which as long as your forking happens inside of the fibers and your debugging code that's outside of the fiber, that would be okay. But if you, I'm not sure how you get a mutex across forked processes. I don't think you can do that across separate processes. So there's still a challenge section, but let's see if we can get this to work. Yeah, I ran for almost 5-6 minutes. Why are you still here? Get it out of my screen. So we said we were going to look at the conditions code, and how does that get implemented here? So we have this new status condition. Okay, ready. So this is the big one here. When we get to the end and we are done reconciling, we write back our status. And at this point, we're in a separate process. We are no longer subservient to the upsert, which may have already exited. Upsert reported on some progress indicating that download began, and so let's look at that code, because that's going to be more interesting than this one. This one, we patch our own entity to say, all right, we're ready now. We've got the value that you've been waiting for. Here it is. Patch it in the status, and that value is this count and the update time, and then the condition that everything is okay. So if we go back to our leaf reconciler, come on. What other conditions can we experience? Well, under deletion, handle deletion. Patch equals handle deletion. So I suppose we want to see when handle deletion gets called, or if it gets called. That's one of our local methods. It's not in the utility box yet. Fetch deletion timestamp. What does that do? It just reads from the metadata. We've not fetched anything. It shouldn't be called fetch. Maybe we're going to call it fetch. Alright, so that just looks to see, is there a deletion timestamp? And if there is, handle deletion. Here is what will return. A new condition terminating false. Status ready false. Reason terminating. Okay. So, did we see that happening? Not sure. We have to turn the cron job back on to see it happening because it's not performing acceptably locally. Not sure why. I have a feeling it's getting into some kind of a loop here, because this is not something I've seen other people implement this way. I may be doing a bad thing, or I may just be doing a new thing that hasn't been thought all the way through yet. So when the delete method gets called, we've got patch status, garbage collecting, terminating true, reconciling, terminating ready false. Handle deletion. Call handle deletion. Patch. Return patch. So this is upsert getting called after delete. I don't think that I want to return any patch at that point. I think that might be the problem, actually. I'm going to put binding.pry right here. See if I do get called here. Fiber, and it's pry I want, not IRB. We've already got pry required there. And I'm going to do one other thing here because Foreman runs separate processes. Like I said, we can't communicate across processes. I'm going to run the leaf reconciler myself in a separate window. So let's see how this goes. So we're going to comment that out. Here we've got bundle exec ruby CLI leaf. We're going to run that. And I don't think that's going to do anything until events start flying. So, all right, make here we'll do make Foreman. I think it's possible that that final patch coming back is what's causing us to get stuck. Because it's constantly patching with a new timestamp and calling upsert every single time. Reach the end for package version. Well, the leaf isn't doing anything this time. Looks like sample isn't doing anything either. Alright, so we get our delete trigger action. Remove finalizer to flagger. Remove finalizer to customize controller. Package versions. Are we getting delete events at all? we get the delete event, remove finalizer, and it gets deleted, and we never get into that method. Let's try it one more time. So this is what we really want here, is this resource should also report on its status. It's going to be challenging because its status depends on other resources, but it can still report on its status as of the last observed generation. So that's what it's supposed to do in the operator pattern. I'm going to give it a cut, paper cut. Doesn't seem like it's working, does it? What if I delete that? Are we not getting the delete event at all? Sample. Looks like that sample controller just isn't running. Well, let's see. Oh, okay, we create a new operator, then we call the sample.ensure method, then we run the operator. That sounds pretty straightforward. So why doesn't that work? Sample.ensure. Are we getting to the end of sample.ensure? We can put a couple of pry statements in here and find out. Let's see. Get project. If k respond to kind. Project is already present on the cluster. Oh, that's how we got stuck then, isn't it? Alright, let's remove the finalizer so this gets cleaned up. And then we'll run it again and see if it works this time. No, I don't want that one. I want leaf to run and the other ones. Control plane is real slow. There it is. Samples created. Okay. Trigger add action for Flux CD. Create new project. We have all of our leaves. Is it going to create one for Helm controller now that we deleted ours? Doesn't look like it. Okay, so it does create the project. So where is our project reconciler? Why isn't it coming back to do something? Hmm? Trigger add action for Helm controller. There we go. Wait, that's PKV sample. Alright, so this does make things a bunch more complicated. Because we've got two measurements going on at the same time now. Alright, let's try and make this less complicated again. I don't want to look at that. Okay. And actually, let's try a clean sweep here. I'm going to assume that it is going to fail if things are wrong, but oh, it did eventually create a Helm controller, huh? Okay, let's see what happened. Fiber is running. Add finalizer to Helm controller in reconcile async. Reconcile async ran database activity. Trigger update action for Helm controller. Upsert called for Helm controller. Leaf upsert was called, but short circuiting, it's already ready. So I think that is how it's supposed to work. We want to see our debugger run. Here. Alright, this should be how it's supposed to look. And then when it gets to the end, it should delete all the resources. If it doesn't, then that means the issue is reproducible. I wonder why this is so slow. those little zombie processes not being cleaned up after? Is that what's happening? Alright, so they didn't become ready. Where's our delete event? Anything get deleted? Oh, that's interesting. Finally gets around to registered health check after everything is done. Yeah, it sure looks like it's calling it an infinite number of times here. Oh, this is not fun. Alright, I'm going to debug this off stream. I'm going to come back when I know what's wrong, and then we're going to figure it out together. But not this painful mess. This is terrible. Okay, friends, it's been a fun hour and a half.